Hello and welcome to my presentation. Today I'm going to talk about dynamic geothermal brine steam separation modelling and non-condensable gas option evaluation towards a digital twin. The project background is shown here. We'll discuss the purpose of the research, look at digital models, shadows and twins, and look at the overall objectives. You can see some pretty black and white pictures here of the real process plant that we were building a digital twin of. This is the NAFA geothermal plant in New Zealand in the top end of the North Island. So the research purpose was to look at using digital twins, digital shadows and digital models to address environmental concerns around energy plant. The geothermal industry is significant in New Zealand. It's part of our renewables portfolio. 80% of our energy is actually generated from renewable energy, of which a significant chunk is geothermal. One of the issues is that some of the geothermal plants are also CO2 emitters through non-condensable gases. NAFA is such a plant, although it's relatively low CO2 emission, it's still finite, about the level of a combined cycle gas turbine. However, there's a lack of specific research on this and lack of digital models in this area. So there's a gap here to try and help understand what's happening. And we're trying to address this by building models. So we're going to be using the term digital model, digital twin in this talk. And this is an overall view of what we mean by that. Typically, a digital twin is where you've got a digital object that is a digital copy or shadow of that physical object, and there's bi-directional flow of data between the physical and digital instances or objects. This is the end point that we're seeking to get to. Very often when people talk about digital twins, they actually mean digital models or digital shadows where there's manual data flow between the two, or only one-way automatic data flow in the case of a digital shadow. Most of what I'll be talking about today, admittedly, will be digital models. So the project objectives are to develop a digital shadow, which requires development of a digital model of that power station that we saw before. We want to develop that model and validate the accuracy of it, then look at using it to optimize the operation of the plant and look at decarbonisation and what we can do with the non-condensable gases using that model. So in terms of progressing towards this digital twin, we developed the model, and so I'll describe the process, how we developed it, and what the overall model looks like. So this is a brief simplified block flow diagram of the process. So we've got brine and steam from production wells that go to an inlet separator where the brine and steam are separated. These are then sent to a vaporizer which exchanges heat with the working fluid, which is normal pentane. And the normal pentane goes through an organic recycle, an organic Rankine cycle, where energy is extracted and via a turbine that is connected to the grid. And the resulting fluid, geothermal fluid, called geothermal fluid, goes through preheaters and is injected back into the geothermal well. So it's quite a complex process. And well, arguably simple and we just look at the BFD, but actually when you start to look at the engineering units involved, it's more complex than one initially would consider. There's several recycles, energy and mass recycles, and the challenge also is getting data from the plant in order to develop good modelling. And so we went through an iterative process to get to our overall final model. So the final model here looks like this, where we're actually modelling the surface facilities from 2 production wells. These are NG28 and NG30, which is shown on the left-hand side of this simulator PFD, which go through SEP1, the inlet separator, where we separate out the brine and the steam. There's several flash vessels, piping and heat exchangers that are simulated in this process, along with a number of level and flow controls that exist in the plant. And then we simulate the re-injection back into the reservoir. So several challenges in doing this, and these are outlined here. So characterizing the geothermal fluid, the conditions around the inlet to the separator, how to develop and model the vaporizer, looking at the control scheme and any other, well, there's a number of other limitations that come out of this. So in terms of the geothermal fluid composition, there was 6 non-condensable components and water. What we found was when we model this in our simulator VMG sim or symmetry, the vapor fraction differed somewhat from the plant, and there was quite a lot of temperature sensitivity. We investigated, therefore, different thermodynamic property packages and did not find much differences between them. So we chose our favorite, which was Pung-Robinson, and handles both polar and non-polar components well. So it handled both the working fluid and the geothermal and brine fluids. This is a similar issue that we saw in previous work on another plant at the same site, and that has been reported in the literature. We ended up by simplifying this to get 2 final non-condensable components and water. For the inlet conditions, again, it was a difficult model to model because of the matching physical phenomena. We just determined that the flow is the most important thing here, and we had 2 wellhead curves, which are shown here for the 2 wells, NG30 and NG28. So there's most of the flow comes from one well, and supplementary flow is provided from the other. So essentially you'd either do flow or pressure control, which will give you the flow that you require. The vaporizer itself, is schematically shown here on the left-hand side. It's a bit of a unique design in that there's 2 sets of tubes within one shell. Steam has 1 pass straight through the vaporizer, but the brine has 2 passes. This type of unique heat exchanger doesn't exist in most simulators, so we model this using 2 coolers and a heater, as shown on the left-hand side. And we could basically use what we know about heat transfer to connect them all together, and we could then do both initially design and then rating type calculations. The working fluid was pentane. We didn't have much historical information from the plant. This is actually a new plant, but we did have 1 base case that we could use, and by playing around with flow rates and so forth, and vaporizer pressures, we can get a reasonable match to that case. The control scheme was quite complex, 26 control loops, but most of these are around basic inventory controls. So what we, in addition to ensuring that we included those, our digital model or digital shadow are focused on 3 key level controllers. The pressure control was by manual operation of the non-condensable gas vent valve, which reflected or reflects what's the practice done in the plant. Several limitations were discovered in the model. Really was good operating at a particular flow rate or thereabouts. And I guess, again, the lack of operating data for the pentane cycle meant that we were using hopefully intelligent guesswork to get good matching. How do we validate it? Well, we did have some plant data. We had data on four variables of interest: the vent temperature for the non-condensables, the outlet temperature of the plant, the reinjection temperature, and the flow rate through the vent of the non-condensables. These, of course, being of commercial interest, so hence they're measured. Most of these were actually pretty good fits from the model. You can see that. However, there was quite a large error on the non-condensable vent flow. And this, we think, is to do around that matching of the thermodynamic packages, and particularly for this case. Where, so what would be required here perhaps is more measurements to really and perhaps tuning of the thermodynamic package to get a better match. But that was outside the scope of this work. So we were reasonably confident we had a good validated model. So we then use this model to look at different control schemes. One of the issues around was the control for the plant initially was the control in the separator level. The problem here is that the original feedback in the plant had the separator level controlled by the reinjection valve, where there's a huge dead time between the separator and the reinjection. And so we were looking to try and get more robust control. The alternative was to move the control back to a valve located much closer to the separator to get a quicker response and obviously minimize that dead time. And then the downstream valve could be used for something else. So we explored that. We also explored the use of cascade control in a preliminary study where we had a level to flow cascade. So the results are sort of shown here from our plant studies, or not the plant studies, our digital twin studies, looking at what the model would show us. And we can see here our alternative scheme gives us a much better control scheme than the original plant control scheme. What is interesting is the cascade control, at least the instantiation that we looked at, did not give us much improvement at all, but that could be tuning or a number of other factors. Interestingly enough, the plant actually decided that, in fact, because it's still stable or stable enough for them, even though there is significant deviation, they were okay with this performance, and so they did not change the level controller valve location. Last but certainly not least, we looked at using the digital model for studying process decarbonisation, particularly looking at the NCGs. So here we would say that there's, looking at this, we looked at variation with respect to outlet pressure and flow rate and how the emissions changed. And if you look at the figures here, you can see it's reasonably flat. There's not a lot of difference, but there is some difference. So there's some room for maneuver. There's obviously a proportional relationship between the flow rate and the gas emissions. This is commercially conflicting. So we need to bear that in mind. So there's a basis of an optimization here between emissions and power production. we looked at some different technologies that could perhaps help us with this. So looking at reinjection, use of CO2 for beverages, for maybe using the stream as a fuel, or for supplying greenhouse gases. CO2 to a greenhouse located nearby. This has precedent in New Zealand, where there is a plant in the middle of North Island, which has greenhouse areas supplied by a local geothermal plant in just this manner. And so the conclusions here that it would be possible or feasible to look at greenhouse close to the plant where the CO2 is supplied from the plant. So this is the content of my presentation. There's lots of work that we can go on to do, but at this time, because of the limited time in this presentation, I'll stop it here, and I'm happy to answer questions. Just before I do open the floor, I'd like to acknowledge my co-authors, and also Rob Kirkpatrick, my colleague, who is also a director of NAFA Generation Limited. Thank you very much for your attention.